Now that we know initialization matters, let's see how we can deal with it. A simple approach would be to initialize weights randomly within a small range. We did that in the minimal example. We used the NumPy method, random uniform, and our range was between -0.1 and 0.1. This approach chooses the values randomly but in a uniform manner. Each one has the exact same probability of being chosen. Equal probability of being selected sounds intuitive, but it is important to stress it. You will soon see why. Really soon. Here's a second approach. We could choose a normal initializer. The idea is basically the same. This time though, we pick the numbers from a zero mean normal distribution. The chosen variance is arbitrary, but should be small. As you can guess, since it follows the normal distribution, values closer to 0 are much more likely to be chosen than other values. An example of such initialization is to draw from a normal distribution with a mean 0 and a standard deviation 0.1. Both methods are somewhat problematic, although they were the norm until 2010. It was just recently that academics came up with a solution. Let's explore the problem. Weights are used in linear combinations. Then the linear combinations are activated. Once more, we will use the sigmoid activator. The sigmoid, as other commonly used nonlinearities, is peculiar around its mean and its extremes. Activation functions take as inputs the linear combination of the units from the previous layer, right? Well, if the weights are too small, this will cause values that fall around this range. In this range, unfortunately, the sigmoid is almost linear. If all our inputs are in this range, which will happen if we use small weights, the sigmoid would not apply a nonlinearity, but a linearity to the linear combination. As we discussed, nonlinearities are essential for deep nets. Conversely, if the values are too large or too small, the sigmoid is almost flat, which causes the output of the sigmoid to be only ones or only zeros, respectively. A static output of the activations minimizes the gradient, while the algorithm is not really trained. So, what we want is a wide range of inputs for the sigmoid. These inputs depend on the weights, so the weights will have to be initialized in a reasonable range, so we have a nice variance along the linear combinations. In the next lesson, we will explore how to do that. Thanks for watching.